All right, so, yes, yes. An interval is what you use to find the area of the curve. We haven't used that word yet, though, so don't worry about it. Okay?
We've used interval a couple times.
The interval, yeah, right. Don't worry about the word interval yet. Okay, so estimate the area for the case B equals pi over 2, taking the sample points to be midpoints and using 4 subintervals. Yesterday we came up with a formula for the area at any point B, but we didn't solve it because we would have had to take a limit to do that. Today we're going to actually do it, okay? And this is going to be a little bit gross because they're making us use the sample points to be the midpoint. Wow. And we want 4 subintervals. So if I take this and cut it in half, this halfway point will be pi over 4. And then I need to cut that in half again, and this one will be pi over 8. And then this one will be
pi over 3 pi.
Yes, 6 pi over 8. 1, 2, 3 pi over 8. What did you say? No, 3 pi over 8. Okay.
I have a...
Okay.
Wait, but B is not at 2 of pi.
Are we using...
B is at pi over 2.
Are we using the equation thing?
No, we're going to use, so what's the widths of all of these little rectangles?
1/8, pi 8.
So the area is going to be the width of all the rectangles, which is pi over 8, times the heights of all the rectangles, and they want us to choose the midpoints to dictate the heights of the rectangles. But that's okay, we're going to do this one first, and then we're going to go from there, right? So this one is, this midpoint is pi over 16, which means this next midpoint is going to be 1, 2, 3 pi over 16. This next midpoint will be 4, 5 pi over 16, and then this midpoint here will be 6, 7 pi over 16.
What does this have to do with anything?
You guys are just way ahead of the game. So 3 pi over 16 is one midpoint, 5 pi over 16 is another midpoint, and 7 pi over 16 is going to be our last one. Okay? Yes. Midpoints are particularly gross, and they threw a trig one at us. Okay? So it's going to be pi over 8 times the cosine of pi over 16 plus the cosine of 3 pi over 16 plus, because we want 4 rectangles, plus the cosine of 5 pi over 16 plus the cosine of 7 pi over 16. Okay? Yeah, way easier. It's called taking the integral, but we don't know that yet. I told you, we just have to sort of suffer through this for the first 2 sections.
We're wasting paper.
Oh my gosh. So just type that into your calculator.
You just want to find the area.
So type that into your calculator.
I don't know how to type my calculator.
My calculator is not working.
You don't know how to type this into your calculator.
No, it's too loud.
Lost my calculator.
Okay, so we need to make sure that you are in radian.
No, I know how to.
And then I'm going to go
Oh, you want the second?
pi over 8 times the cosine of, what was the first one? Pi over 16? Pi over 16 plus the cosine of 3 pi over 16 plus the cosine of 5 pi over 16 plus the cosine of 7 pi over 16. Close my parentheses, close my parentheses. So my final answer for the area of that little sector is about 1.006.
So that's not what I got. Area. Well, 1 point. You got that.
Okay? Any questions?
Are we done?
We're done with that problem, yeah.
No, I can't go back.
Okay.
It's ridiculous.
It's not a circle. It looks circular, yeah, but it's not circular. I yelled.
Yeah.
Gunner, what's your problem? Come on! What?
Yeah, I do.
Oh, so what you're wanting to say is you want to make this be some sort of a square, right? With this area would be pi over 2. And then that's like 3/4 of that?
No.
Alright, whatever. Okay, moving on. Now let's consider the distance problem. Okay? So at the very beginning of the section / chapter, we said, you probably don't remember, that we were going to, in this section, we discovered that in trying to find the area under a curve or the distance traveled by a car, we end up with the same special type of limit. Okay? So we're kind of done with the area underneath the curve part.
No,
I mean,
no.
just for
But
now.
I don't get that because you know how much a car travels.
How do you know?
Because
you're in the
you were in the car.
What if you're not in the car? Ha! Gotcha.
And you look
Okay,
it up on a
so
map.
now let's consider the distance
GPS.
problem. Find the distance traveled by an object during a certain time period if the velocity of the object is known at all times, okay? So, Leanne, what we're going with is a situation where we know the speed of the object but not the distance that it has traveled, and we're going to try and find the distance traveled, okay? And hopefully what you guys sort of recognize is this is the opposite of what we did in the previous chapters. What we did before is we knew what the distance time graph looked like, right? And then we were able to figure out its velocity. Right, we figured out the instantaneous velocity by taking the derivative. So there is a connection there, okay? If the velocity remains constant, then the distance problem is easy to solve by means of the formula distance equals rate times times. But, this is calculus, if the velocity varies, it's not so easy to find the distance traveled. We investigate the problem in the following example, okay?
Can I write this down?
Yeah, so this is an example that you might want to write down as I read it. Suppose, Evan, the odometer on our car is broken.
What's the speed odometer?
That's
The
actually-
odometer says how far you've gone. And we want to estimate the distance driven over a 30-second time interval.
Then you go to the dealership and get it fixed.
We take speedometer readings every 5 seconds and record them in
That's
the
way too much
following
work.
tables.
Okay, if you're looking at 5 seconds, you are taking your eyes.
So since over here we had time in seconds and our velocity was in miles per hour, we want to get that to be consistent. And so using the conversion that 1 mile per hour equals 5,280,
Why would they just give that to us in the
Oh my
first
God, why do you guys just fight and fight and fight and fight?
Because this book is stupid.
questioning the
Anyway, so this is that table reworked where the velocity is now in feet per second.
So now my whole middle column like doesn't move.
Just add one more thing on there.
Yeah, but that whole
No,
thing.
yeah, but why, if they're just gonna give it to us, just give it to us in the first place.
Yeah.
This is supposed to be like continuous.
So here's how it goes. No, but if you're already that high strung about.
What's my element, like we did
Okay,
before?
during the first 5 seconds, the velocity doesn't change very much, so we can estimate the distance traveled during that time by assuming that the velocity is constant. If we take the velocity during that time interval to be the initial velocity of 25 feet per second, then we can obtain the approximate distance traveled during the first 5 seconds. So 25 times 5 is 125 feet. So they're saying, let's just keep this as that, ignore the 31 altogether, and in the first 5 seconds, if you're going about 25 feet per second, then that means that you have traveled about 125 feet.
It seems like
What they're
terrible
doing
math.
here is trying to make a connection between what we did with the curve. They're saying in the first 5 seconds, if our initial velocity was 25 and then our velocity after that was some other number, they're saying let's draw a rectangle using
just say
the
it's
left
29.
thing and say so far we've traveled 125
So
feet.
from 5.
So we're
Okay,
not
okay, keep
underestimating.
going. Similarly, during the second time interval, the velocity is approximately constant, and we take it to be the velocity when t equals 5 seconds. So our estimate for the distance traveled from 5 to 10 seconds would be what you get when you multiply those together, or 155. So they're again drawing a rectangle. They're saying, okay, the velocity at 10 seconds is a little bit higher, but it's pretty close. So let's just draw a rectangle there and multiply those together and get 155 feet traveled in the next 5 seconds. Okay? You see what they got going here?
Yeah, and then you'll do the.
Okay, if we had similar estimates for the other time intervals, we obtain an estimate for the total distance traveled as being 1,135 feet. So what they continue to do then is they said, okay, from 10 to 15, this is going to be another rectangle with a base of 5, and this time the height will be 35, right? So 5 times 35 is, spacing out, 175? That doesn't seem right. Okay, so they would be 175 feet in this interval from 10 to 15 seconds. And then to find how far they traveled from 15 to 20 seconds, they're going to go 5 times 43, right? And then to figure out how far from 20 to 25, they're going to go 5 times 47, which is 235. And then to figure out from 25 to 30, they're going to go 5 times 46 and get that's 235, and get 230. And then if you add these 1, 2, 3, 4, 5, 6 rectangle areas together, you get a final answer of this right here. Okay? So again, they're just, I guess that's bad math. You could do better than that, but they're trying to make a connection between the area under the curve problem and the distance traveled problem. Okay? Don't shoot the messenger.
So did we do one? Well, you go-
Teaching what you're supposed to think. Okay, we could just as well have used the velocity at the end of each time period instead of the velocity at the beginning as our assumed constant velocity. Then our estimate would be, somebody said we were going for an underestimate. In that case, this would be an overestimate, because now you would be drawing your rectangles like this. So I would go up above the velocity points right there. Okay, see what I got going there? When here is my actual velocity like this, so now my rectangle would be above whatever that curve looks like. So we would get a higher estimate this time of 1,215 feet. And so that would be like taking the rectangles from the right-hand side. We did the left-hand side already. From the first one was these rectangles here. We drew up to the left side of the rectangle touched the curve. With these green rectangles, the right side of the rectangles touches the curve. Okay, so that's going to give us a little bit of a overestimate. Okay. All right, and so here's the connection that we are trying to make. Perhaps the calculations in example 4 remind you of the sums we used earlier to estimate areas. I had to give away the punchline because you guys were going to fight me or something. The similarities explained when we sketch a graph of the velocity function of the car in figure 15 and draw rectangles whose heights are the initial velocities for each time interval. So this example right here would be right hand or left hand?
Right.
The right side of each rectangle. Oh, am I facing the wrong way? Oh, sorry, it's because I'm facing this way. Okay, sorry. The left side of each rectangle touches the curve, okay? So this would be our left-hand approximation, okay? And so that's why they use L6 there, because it's the left-hand side, all right? So there's a little connection between finding the area underneath the curve and finding the distance that a car has traveled if you know the velocity. Okay, so just 4 problems for you to work on. The first one, they give you the graph, and then you have to draw in the rectangles the way that you are told, and using the number of rectangles they want you to use, and use those to find the area. 3 and 5, sorry, they're giving you the equation, okay, and you have to figure out the area underneath. So that would be something like what we started the class with right here. Okay, in fact, this is one of the equations that they give you, but they want you to use the right-hand rectangles instead, okay? And then the last one is a problem real similar to this, where you are given some velocity data, and you need to use that to figure out the distance traveled, okay? So only 4 of them. I know the assignment is going to take you a little bit of time because there's lots of just drawing rectangles and plugging in numbers and stuff like that. I apologize for that, but you're going to be okay, all right?
You should have.
I don't know why everyone